Okay, so this video is going to be all about one of my favorite tools in all of mathematics, just about, certainly in all of linear algebra, called the singular value decomposition, or the SVD. So this is the last piece of mathematical theory that we need to talk about, the SVD. And I'm going to tell you what it is and then tell you why it's cool as well. So there's a long theorem here about the mighty SVD, and it looks like this. So it says that any non-square, not necessarily square, m by n real matrix A can be factored into a product of three different matrices. So you can factorize the matrix A into U times S times V transpose, where U is an orthogonal matrix, V is an orthogonal matrix, and S is a diagonal matrix. So it's diagonal, so it's 0 everywhere except for the non-negative diagonal elements, and we call those singular values. Right. We also call the vectors in the matrices U and V, we call those singular vectors, called left and right singular vectors. The ones in U are left singular vectors, the ones in V are called right singular vectors. They're important for different reasons, which you can get into some other time. In MATLAB or in most programming languages, you can calculate this thing. It's so ubiquitous that you can calculate with just one command. It's a pretty common thing. So that's a lot of theory. It might seem a little bit reminiscent to you, maybe, of something that you've learnt before in linear algebra. And if so, that's good. It is very reminiscent of eigenvectors. And in fact, the SVD is essentially just diagonalization for non-square matrices. So that's a really powerful thing. And actually, it allows us to do some powerful stuff. So, I mean, you may remember one cool thing about diagonalization was that we could use it to calculate the inverses of matrices, and we can do the exact same thing with the SVD. So the idea of the SVD is that I can write my matrix, I can factorize my matrix into U times S times V transpose, and the nice thing there is that if A is a square matrix, I can calculate its inverse by doing this, and then I can do, write this as V transpose inverse times S inverse times U inverse. As U and V are orthogonal matrices, it turns out that they turn into, that the inverse of U is just U transpose, and the inverse of V is the inverse of V transpose is just V. And so you can write the inverse of A as just this, and even better, S inverse here, well, because S is a diagonal matrix, this just turns out to be 1 over sigma 1, 1 over sigma 2, 1 over sigma 3, all the way down to 1 over sigma n, with zeros everywhere else there. So actually, this turns out to be, just as diagonalization was a really efficient way of factorizing matrix and finding its inverse, it's exactly the same for the singular value decomposition. And actually, that idea gives us a whole lot of other things as well. So it turns out that some consequences of this SVD are that, if I have a symmetric, positive, semi-definite matrix, so thinking back to that, what that term means from earlier, then the singular values are the eigenvalues. You can choose, U and V are exactly the same, and the singular vectors are the eigenvectors. So this singular value decomposition, it really is a generalization of diagonalization, of finding the eigenvalues and the eigenvectors of a matrix. Is a generalization to non-square matrices. So if you've been convinced in the past that diagonalization is a useful thing to do to square matrices, then hopefully you should be able to see that doing a singular value decomposition for a general matrix is also a really useful thing to do. And it is. It's incredibly useful. It turns out that this SVD is the basis of a lot of things in machine learning. So, for example, principal component analysis, if you've heard of that, is essentially a singular value decomposition. So in data science, that's a really useful statistical tool to use. It turns out it has come up in all sorts of different places. So in fact, Netflix uses the singular value decomposition. So so netflixprize.com is a website you can go to. It's an old competition now. So in 2009, Netflix proposed this $1 million prize to find the most efficient way to recommend new videos, new movies to people on Netflix. So given somebody's history of the things that they'd watched on Netflix, can you predict what they're going to watch next? And it turns out that the grand prize, the $1 million prize, was won by somebody who used the SVD. So they wrote a paper on it that you can look up that looks like this, so matrix factorization techniques and recommender systems. And basically what it did is it took all of the data that Netflix gave in the competition, so a giant matrix of all of the recommendations, so where rows of people and columns are titles of movies, so all the data on things that individuals had watched, and did a matrix factorization, did a singular value decomposition on it, and then it turned out that would be a great recommendation system. So here's how it sort of worked. So you had data that looked like this. So you had a whole bunch of 480,000 users, and then the history of movies that they'd watched. And essentially what they did is they took this matrix, with all of this sparse matrix with all of these numbers in it, and factorized it. So wrote it as something like this singular value decomposition, something very, very close to a singular value decomposition. The details, the differences don't really matter. And then what they did, so this is a paper from their, this is a figure from their paper. What those vectors gave them is if you plotted the first couple of vectors from that matrix decomposition against each other, you got a sort of landscape of movies. And movies that similar people had watched tended to cluster close together. So from this, you could come up with a recommendation algorithm. So if you liked the sound of music, right, then there was a good chance something close here you're going to like as well. So you might like Sister Act as well. Or if you liked The Fast and the Furious, then you're probably going to like Armageddon or something like this. The Wizard of Oz is in the middle because everybody likes The Wizard of Oz. Here's the indie region up here. If you liked Wes Anderson, then you probably like Being John Malkovich or Lost in Translation as well. Here are sort of, if you liked Natural Born Killers, you'd like Kill Bill as well. And this actually works for clustering movies that were recommended or that were liked by, were similarly liked by people together. So it all is based on this singular value decomposition. So it's a really powerful tool. We will see it a lot throughout the course. It is much more ubiquitous than you think.